If retrieval is an active process that modifies stored information, what happens to the memory trace after it is put back in the brain? One suggestion is that retrieved memories, just like newly acquired information, are labile. In order to become stable, they must undergo a second consolidation phase, now called reconsolidation. The first systematic investigation of reconsolidation used a simple paradigm in which rats hear a tone and then experience a brief foot shock. The next day, the animals freeze when they hear the tone, indicating that they remember the sequence of events. If a protein synthesis inhibitor is administered immediately after the test tone, the freezing response disappears on subsequent tests. Protein synthesis inhibitors disrupt the initial consolidation phase, and these new data suggest that a similar process occurs during memory retrieval. Post-retrieval modification of memory has been demonstrated in other species including worms, mice, and humans. See Figure 3.5. Previously consolidated memories, therefore, may undergo a second phase of instability when they are retrieved. Despite the apparent similarities, reconsolidation is not just a second consolidation, as the two processes involve different biological mechanisms. Figure 3.5. Experimental paradigm to test reconsolidation of memory. A to C. Memory consolidation depends on protein synthesis. A. In a single conditioning session, rats are presented with a light followed by a mild foot shock. The next day, rats freeze and the light is turned on. No shock is presented. B. Administration of the protein synthesis inhibitor, anisomycin, immediately following conditioning blocks the freezing response on day 2. C. If anisomycin is administered 3 to 4 hours after conditioning, freezing remains intact. D to E. Memory reconsolidation depends on protein synthesis. D. Rats undergo conditioning and testing sessions as in A. Following testing, when animals freeze, they are injected with the anisomycin. In a subsequent test, 24 hours later, rats do not freeze. E. Rats freeze on the second test if anisomycin is injected 3 to 4 hours after the first test session. Okay, so from the diagrams, you can see that if they're just shocked, then the next time they will freeze. But if they're immediately injected with anisomycin afterward, they won't freeze 24 hours later. But if they're injected with anisomycin 3 to 4 hours after they are shocked, it's too late and they will still freeze the second day. Oh, okay, the last two diagrams are really interesting because they deal with the same process for reconsolidation. So if the rat is shocked and then they're tested the next day, they will freeze. But then if they're immediately injected with anisomycin to block the protein synthesis, they won't freeze the next day. But of course, if the same process occurs, but they're injected with anisomycin 3 to 4 hours after the new shock and freeze, they will still freeze. Okay, so you really can change a reconsolidated memory by injecting the anisomycin, which stops the protein synthesis the second time when the memory is revisited. That's super interesting. It really is labile or flexible even the second time you pull it out of your mind. Not all evidence supports the concept of reconsolidation, although negative findings in these experiments can be difficult to interpret. At the very least, it might be too simplistic to assume that an established memory can be erased with protein synthesis inhibitors. No doubt there are restrictions on how and when memories are altered during retrieval, but this does not detract from evidence that information accessed from memory stores is subject to changes. Working memory. Early descriptions of memory, some going back thousands of years, make a distinction between short and long-term memory. Short-term memory was described as a time-dependent process with limited capacity. For humans, this is the information held in immediate consciousness, or the small number of items that can be remembered over a short period of time. It's about 2 seconds. Definition and description. An interest in studying this process emerged in the 1950s with the rise of cognitive psychology and the recognition that keeping information in conscious awareness involves mental effort. Atkinson and Schriffen, 1978, formulated one of the first models explaining how incoming information is organized in the short term before being transferred to long-term memory. They used the term working memory to describe the temporary buffer that provides a gateway to permanent storage. The concept evolved over the next 2 decades with an increased emphasis on the active or dynamic aspects of working memory and how these contribute to cognition. Badley and Hitch, 1974. Although there is still some disagreement on the specific components, a contemporary definition of working memory is the process of maintaining information in short-term store so that it can be used in other cognitive processes. A primary distinction between the original and updated definitions of working memory is that the latter incorporates knowledge acquired during previous experiences. In other words, working memory is an ongoing mental computation that uses recently encoded information and information retrieved from long-term store to make decisions, navigate in space, or communicate with conspecifics. Because working memory holds information online as source material for other operations, it is sometimes described as the brain version of random access memory, RAM, in a computer. Working memory tasks. One of the best ways to understand working memory is through a working memory task, such as the N-back task shown in Figure 3.6, one of the most common laboratory measures of working memory in humans. In a real test, these letter stimuli would be presented one at a time, either as visual images or by having someone read them aloud. Participants are instructed to identify stimuli which match a stimulus presented n steps earlier in the sequence. Obviously, increasing the value of n increases the difficulty of the task. To perform efficiently, participants need to keep recently presented stimuli in mind and compare these to previously acquired information about the alphabet. Patients with neurodegenerative disorders, such as Alzheimer's disease, may have no problem naming letters. Indeed, many can still read, but their performance on the N-back task is dismal, even when n equals 2. This pattern of deficits is even more pronounced in patients with prefrontal cortex damage, who show no amnesia for previous events, but dramatic impairments in working memory. This suggests that retrieval of information from long-term store is distinct from the ability to use this information in ongoing cognitive processing. Figure 3.6. Experimental design of an N-back test. Stimuli are presented on a computer screen, one at a time, with a variable time delay between stimulus presentations. Subjects are instructed to respond, e.g. touch the screen or press a spacebar, when the current stimulus matches the stimulus N positions back. Okay, so there's a diagram. It says presentation time 1000 milliseconds, and the interstimulus interval is 600 milliseconds between letters, and this is an N3 task. Okay, so it's a series of letters, and you just want to know the 3 letters shown before, and this is a string of A's and H's. A critical feature of working memory tasks, including the N-back, is that the information which subjects must use to make a correct response varies from trial to trial. This introduces an element of unpredictability, both in terms of time and content. The principle has been applied to animal tests, allowing researchers to examine working memory in different species. Most of these tests take the form of a delayed matching task in which animals are shown a sample stimulus, such as a small plastic object, for a brief period of time. Following a delay in which the stimulus is no longer visible, subjects must identify which of 2 stimuli matches the original. Working memory is activated because subjects must keep information about the sample stimulus online during the delay. The task was originally conducted with primates using an apparatus like the one shown in Figure 3.7. A modern version uses a computer screen and automatic reward dispenser. Not surprisingly, Accuracy declines with increasing delay periods in a variety of species. Distracting animals during the delay period also reduces correct responses because they lose information held in working memory. Figure 3.7, Wisconsin General Test Apparatus for assessing working memory in primates. An animal sits in front of a tray that contains recessed food wells at one end of the apparatus. An experimenter sitting at the other end of the apparatus places a sample stimulus over one of the food wells while the animal watches. A screen blocks the animal's view, and the experimenter replaces the original stimulus with two stimuli, one that is the same as the original and one that is different. After a variable period, the screen is raised and animals are rewarded for choosing the matching stimulus. In a modified version of the task, animals are rewarded for selecting the new or non-matching stimulus. Okay, so in the diagram you can see you have a monkey, and then you have a movable screen, and then a stimulus tray, and you have a guy sitting at a chair next to the one-way vision screen. Experiments using the delayed matching paradigm suggest that working memory is better, i.e. longer and larger capacity, in humans than in animals. Data from a single paradigm, however, are never sufficient to establish a truth. Indeed, a challenge to the notion that working memory is limited in animals arose when the radial arm maze paradigm was developed for rats. Olson and Samuelson, 1976. See Figure 3.8. On each trial, rats are placed in a central platform and are allowed to search the entire maze to find food rewards. These are placed in small wells at the end of each arm, so they are not visible from the central platform. Rats quickly learn to retrieve all of the food without revisiting the same arms twice, even in mazes with 24 arms. To perform accurately, rats must be updating information constantly about which arms no longer contain food. The working memory component of the task can be increased by inserting a delay between arm visits. As an example, after a rat has retrieved 4 out of 8 food rewards and returned to the central platform, they are restricted from entering the alleys by doors that are inserted at each entranceway. In some experiments, rats are removed from the maze completely. After a delay, the doors are removed and rats are allowed to retrieve the remaining food. An error is scored if a rat enters an arm from which it already retrieved the food, either before or after the delay. Rats exhibit much better working memory in the radial arm maze than in typical delayed response tasks using visual stimuli and a computer screen. In some cases, rats can remember which arms they visited up to 24 hours later. Figure 3.8, Radial Arm Maze Paradigm for Assessing Working Memory in Rats. A. Animals are placed in the center compartment of an 8-arm maze with doors to each alley closed. A food pellet is placed in 4 randomly selected arms. The same arms are continually baited for each rat. At the start of a trial, the doors are opened and rats are allowed to explore the entire maze. Rats cannot see the food until they reach the end of the arm, but over trials, they learn which arms contain food and visit all 4 arms in an orderly fashion without entering the non-baited arms. In a working memory trial, rats are allowed to retrieve 2 of the pellets and then are confined to the center compartment. After a delay period, the doors are opened so animals can access the entire maze. B. As the time confined to the center increases, animals make more arm revisits, defined as returning to a previously baited arm where they have already retrieved the food. Okay, so in the diagram you can see this contraption. It's kind of cool. So there's like a central pillar where the rat is, and there's all these arms, and the rat can't see whether the food is at the end of the arm until they're in the compartment at the ends. It's symmetrical, really cool. Then we have a graph. On the x-axis is time confined to center, and on the y-axis is arm revisits. Okay, so you can see that the time they're confined to the center as it goes up, they revisit the arms more, showing that their working memory is declining. Evolution of working memory. There are a number of reasons that working memory appears to be much better in the radial arm maze than in delayed response tasks, Shuttleworth 2009. One of the most obvious is that searching for food in a maze mimics foraging in the natural environment, so rats have a natural tendency to perform in this task. Researchers have taken advantage of this, adapting the radial arm maze to reveal working memory abilities in birds, Broadbeck 1994, dogs, and insects. The existence of working memory in these different species should not be surprising, as all animals face ecological challenges that require the updating of environmental information, such as the location of food sources. Even with exceptionally long-term memory storage, animals would have difficulty using this information effectively if they could not keep track of ongoing changes in their environment, such as when food in one location is depleted. The main difference in working memory across species is how much information can be kept online and how well it can be used in other cognitive tasks. Both honeybees, Apis mellifera, and fruit flies exhibit working memory in a delayed response task that lasts up to 5 seconds. Performance declines even at this short interval, however, if another stimulus, i.e. a distractor, is presented during the delay. Insects have tiny brains, approximately 1/millionth the size of a human brain, and almost all of it is devoted to detecting and processing sensory input. Cognitive resources available for working memory, therefore, are restricted. It is too simplistic to conclude from these data that larger brains mean larger working memory capacity. At least in mammals, a critical component of working memory is neural activity in the frontal lobe, particularly the prefrontal cortex. See Box 3.3. Box 3.3. How does the brain control working memory? The contemporary definition of working memory was not formulated until the 1980s, but, long before that time, clinicians and scientists speculated that the frontal lobes were critical for this process. One of the most famous patients in neurological history, Phineas Gage, was described as devising plans that he was unable or unwilling to execute after an accident destroyed a portion of his frontal lobe, Harlow, 1868. Close to 100 years later, surgical removal of one frontal lobe left a woman unable to carry out the sequence of tasks necessary to prepare dinner, Penfield and Evans, 1935. These case studies, replicated in later clinical reports, identified a subregion of the frontal lobes, the prefrontal cortex, as important for keeping track of ongoing changes in environmental input, i.e. working memory. These human studies confirmed prior animal experiments showing that monkeys, Cebus apella, with prefrontal cortex lesions were unable to remember the location of a food reward for more than a few seconds. Jacobson, 1935. Researchers then proceeded to examine what happens in the prefrontal cortex when animals perform a delayed response task. Recording cellular activity within this region revealed that prefrontal neurons began to fire when the sample stimulus was presented and then continued to fire when it was removed. That is, neurons within the prefrontal cortex were active during the delay period when subjects must keep a record of the stimulus in working memory. More detailed anatomical work showed that neuronal activity increased in different areas of the prefrontal cortex when rhesus monkeys, Macaca mulata, were required to remember a spatial location versus an object. Most importantly, if the firing of a neuron was not maintained across a delay, either because the delay interval was too long or a distractor stimulus was presented, the animal was very likely to make an error during the choice phase. See Figure 3.9. This suggested that the active process of keeping information in short-term store is mediated by neuronal activity in the prefrontal cortex, a finding confirmed in brain imaging studies with humans, Courtney et al., 1998. Figure 3.9, Neural basis of working memory. Electrophysiological recordings of prefrontal cortex, PFC, neurons are obtained while monkeys perform a working memory task on a computer screen. A. During the initial intertrial interval, ITI, monkeys fixate on a visual stimulus in the center of the screen. 5 seconds later, an array of visual stimuli are presented, 0.5 seconds, around the periphery of the screen with one stimulus target marked in a different color. The stimuli disappear for a 1 to 6 second delay period, during which time animals must continue to fixate on the central stimulus. When the central stimulus disappears, animals are rewarded if they make an eye saccade to the previous location of the target stimulus. B. PFC neurons fire during the delay period, when animals must maintain the location of the target stimulus in working memory. The top panel shows firing patterns of individual neurons across time. The bottom panel shows the combined activity during ITI, the intertrial interval, target presentation, delay period, and when animals are making a response. Incorrect responses are characterized by decreased neuronal firing. Okay, so in A you can see the thing at the center of the screen you're supposed to look at, and then there's like squares around the screen and one is a different color, okay, and then there's a delay of 1 to 6 seconds, okay, and then the monkey is rewarded if they look back up at the blank screen where the different colored object used to be, okay. Okay, this is super interesting. So you can see when the target is presented, the neurons start firing more, and they continue to fire more during the delay, and they continue to fire through to the response.